Hi everybody, this is David Barrick speaking. I'd like to do a quick walkthrough of the VPP IP FIB implementation. Now, before we even start looking at code, it's fair to say that the IP4 and IP6 FIBs are very symmetric, that in terms of node names, adjacency handling, and table IDs, they follow a very predictable, similar pattern that with the exception of the lookup method in use, which in the case of IP4 is a 4x8 mtry walk, and in the case of IP6, which is a bounded index extensible hash lookup across the active prefixes, the two FIBs are really basically identical. So if you kind of get one, you'll probably kind of get the other. The only extent to which that wouldn't be true is if you're planning to really replace the FIB implementation, which is a fairly advanced topic. I wouldn't go there, until I was pretty sure I knew what I was up to. At any rate, the typical packet flow for IP packets is that the driver will enqueue packets more or less directly to IP4 or IP6 input. In the case of IP4, input node checksum if the hardware has already validated the IP4 header checksum. Thereafter, packets that survive the input checks will end up going to IP4 or IP6 lookup to most typically IP4 or IP6 rewrite transit for transit switch packets, rewrite local for locally addressed packets, then most commonly to an interface output routine and to interface TX routine, graph node, whatever, which actually dives down into the device driver for the physical hardware. Now, the first thing to say is that there are a couple of degrees of freedom built into the adjacencies, which are actually pretty interesting. Let's look at IP4 forward.c, VNet, IP4 forward. Let's see. Okay, IP4 lookup inline is the main lookup engine. As is typical with code like this, you're better off actually looking at the single loop rather than looking at the prefetching and so on. That's its own kind of, deal. Any rate, P0 is the packet in hand. IP0 is the IP header for that packet. Notice that the driver and or Ethernet graph nodes will have advanced the header by most commonly 14 octets, aka the size of a Ethernet header T. At any rate, so look at the IP packet. The FIB index computation is actually pretty interesting in the following sense. Normally you look up packets based on the VRF or FIB that the interface has been placed into. Howsoever, we built here a control to allow code that wishes to deliberately change VRFs to change FIBs to set VNet buffer of the packet software IF index sub vlib_tx to the FIB index that you want to use. This is the one clock cycle way of doing route leaking cases, of doing specialized lookups where you've received a packet in one VRF in one table based on interface, and then you want to go actually do the lookup machinations elsewhere. Pretty typical in tunnel cases where you may receive a packet, decide by adjacency to tunnel it, and then to use the default VRF. That's certainly the MPLS over GRE story. But at any rate, so long story made long, we determine the FIB index here. Then we'll go do some figuring out if it's IP, so on and so forth. The IP4 FIB mtry lookup step game is taking the four potentially probes into into the IP4 mtry. Now notice the way the tri-walker works is that if you hit a terminal entry like a slant 8, which you'll hit in the top table, you may well do 3 stages of I already have it, I'm not going to do very much. But at any rate, the IP4 FIB has been pretty carefully tuned. It is not notoriously thread safe. It's just merely really fast for lookups. That's an area we need to work on at some point. This IP4 FIB lookup with table guy uses a very completely straightforward, simple set of training wheels which is to say hash tables at each possible destination width as a check. That used to be when VPP was exclusively the punt inject path for hardware forwarded engine. That used to be the IP4 FIB. Well, couldn't really continue with that, but at any rate, it's still around, it's still maintained, and it's still a really pretty darn useful consistency check. Again, asserts only happen in debug images. So if you're wondering why the debug images are relatively slow, this is one amongst many reasons. Here we actually get out of, and the result of the FIB lookup is this adjacency index. And here we actually get hold of the adjacency object itself. Right on this line here is a key degree of freedom in the IP adjacency. We'll go look at the adjacency structure in a minute, but at any rate, adjacencies end up having two specific degrees of freedom built into them to make them very general. One of them is to say, okay, after you've hit on a particular subnet or a particular slant 32 or whatever table entry you hit on, the adjacency, the related adjacency says, okay, now send the packet over here. So you can build, entirely different behaviors without actually touching the IP lookup or rewrite engine by just simply creating adjacencies that have lookup next index. And we'll see when we get to the packet rewriter, you'll see that the rewrite portion of the IP adjacency also has a rewrite next index, so that you can do things like put unrouted table encap headers into an adjacency, have it paint on an outer IP with a packet length of 0, and then at rewrite next index time, you can send it to a node that'll get the packet length to be actually correct and get, for example, the IP4 checksum to be correct. But at any rate, so here's one of the degrees of freedom where you say, okay, you've hit on an adjacency, and now next 0, the disposition or the graph node next coming out of IP4 lookup, it ends up being dug out of the adjacency. Now notice, of course, that this makes the drop cases, punt cases, ARP cases be absolutely identical from the point of view of the lookup engine, that it doesn't have, if I'm trying to do this, then if I'm trying to do that. Rather, it says, oh, you hit on an adjacency, fine, go use lookup next index to decide where to send the traffic. Multipath adjacencies end up being a dense block of adjacencies, which in the case where the adjacency you dug up has more than one chunk in the block, it'll go offer to do a flow hash so that you get correct equal and unequal cost multipath handling. The multipath stuff is a more advanced topic and probably not worth going into on a first path through the code. But at any rate, suffice it to say that if you're doing a multipath adjacency, you simply pick the instance based on the flow hash. Otherwise, you remember the adjacency index that you hit on in the buffer metadata, increment a counter, and ultimately push the packet forward into the graph to wherever it's going. Now, vlib increment combined counter is actually somewhat interesting. If we go look at vlib counter.h, we'll see that there's a per CPU, quotation fingers mini counter, which is actually 16-bit counter, which are incremented non-atomically per CPU. And then if it turns out that the counters rolled over, we do a sync, fetch and add. So for counting packets, for example, every 65,000 packets, you'll do a single atomic op to a shared 64-bit counter. That's a simple counter. The combined counters have, RX, RX or and or TX packets and bytes combined together. But at any rate, that's one of the more interesting performance determinants. That the more threads you run, the more important it is to not be hammering the counters with a continuous stream of atomic ops. You'll recognize this as, as an inline version of the dispatch speculation. This is the single packet at a time case where you need to unwind one chunk's worth of speculation. So at any rate, let's go look here. Right, we missed anything? Yeah, we should probably look at the IP adjacency T for a minute. You'll notice that there's, some dispositions, but the adjacency itself is fairly straightforward. It consists of a rewrite, which is declared via the vnet declare rewrite macro, a certain amount of metadata pursuant to the topics we were talking about earlier. Lookup next index being one of them, being the interesting one that I've talked about. Now, vnet declare rewrite, you'll see, let's see, vnet, it's in rewrite.h. And you'll see that it has, again, a next index, which is the place the packet goes after the rewrite's done. So in a typical case, it's important to be able to locate these structures. Rewrite.h is in vnet rewrite.h, and the IP adjacency lookup. The IP adjacency itself is in vnet IP lookup.h. So this is a specific kind of adjacency. You can imagine, if you're implementing different address family, whatever, you can imagine making more of them. The IP adjacencies are in fact shared between v4 and v6. That the rewrite string contents will obviously be different, but the adjacencies themselves really don't differ at all. Now, the point I've been making repeatedly is that if a certain subnet is supposed to be reached by a tunnel, that subnet's adjacency might consist of an unrouted outer IP datagram with a pre-computed checksum for a zero-length packet. Next index points to a specific kind of post-rewrite node, and it ends up inserting the correct packet length and fixing the IP4 header checksum. There are a number of good examples. Let's take a quick look at the VXLAN code. And you'll see you'll see this is the piece of code in VXLAN, VPP vnet VXLAN VXLAN.c that actually builds the outer IP and pre-computes the checksum. The thing to know is this vec validate align, and noticing that we're creating an align vector, which is the effectively the rewrite string. We know how long it's going to be. This vector will be instantaneously full of zeros, so any field we don't set in it is zero. For example, in this case, we're sticking the hex 45, and what you'll see if you look at the string is 45000000 in the rewrite string. To be fixed up, post. Okay, let's look for encap.c, post. All right, VXLAN and cap. This will be the guy that'll paint it on and then fix the checksum. What do we do? Yeah, we end up as I said, painting on the rewrite we just generated, and then, well, my sense of humor precedes me. I don't particularly love IP checksums. They're kind of the bane of everyone's existence, and this coding pattern here is how to fix the IP checksum. The IP checksum IPC sum update operator is pretty carefully hand-coded by my buddy Elliot Dresselhaus so that it's actually reasonably snappy. But at any rate, here's a case where you put an adjacency into the fib, which has the rewrite next index pointed at this guy. And well, let's see, VXLAN and cap. Right. Yeah, the VXLAN and cap node paints on that, paints on that rewrite string, and then off you go. At any rate, I guess we already talked about the vlib_tx interpretation. That's moderately important. We already talked about the counters. Now let's look at the standard rewriter, which is to say, the standard rewriter, again, look at the single loop. It's the easy way to navigate the code. This ADJRX-TX has to do with rewriting local, rewriting local versus rewriting transit. In the transit case, you're going to be looking at the TX adjacency for sure. Here you get locally received packets, yada, 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 yada. Okay, this is rather a key detail. So what we've done is we've dug out of the buffer metadata the adjacency index, and now we're going to go paint the rewrite string. VNet rewrite 1 header is quite smart about painting rewrites exactly of size, size of Ethernet header T, meaning 14. The interesting thing about the generic rewrite painter is that it tries to do things at least 8 octets at a time, and that's great until what you end up doing is a reverse copy with 2 pad octets, which just happen to spill into another cache line. The point there being that that cache line just preceded. Okay, let me describe it better. Which is to say, when you're rewriting, when you're doing simple IPv4 forwarding, simplest kind of IPv4 forwarding, the NICs, with one noted exception, will DMA the Ethernet header directly onto a cache line boundary. That that the 0th octet will be the first octet of the destination MAC address, and that's great. So now you'll go in, you'll hop down. Say you're just hopping down to IP4. You'll say, oh yeah, I know how to reach that guy. I need to paint on a different rewrite string. The last thing in the world you want to do is to paint on 2 octets into the previous cache line, knowing full well that they're just pads to make the copy appear to be more efficient. The point is that it's way better to do an 8-byte copy, a 4-byte copy, and a 2-byte copy than it is to spill and do 2 8-byte copies, the second of which, or the first of which, depending the order, spills 2 octets into the previous cache line, which has not been prefetched. Even if it was prefetched, it would double the pressure on the load store unit. So yeah, really don't want to do that. And if we take a look at VNet rewrite 1 header, I'll leave it to you to actually go take a look at it. You'll notice that it's real smart about that particular size, because in fact that's the most common size you're rewriting. That you just badly don't want to do a pad operation that spills back into the previous cache line. I was just astounded at how much of a performance difference that made. It was sort of a 7 or 8% difference for one very simple 5-line chunk of code. You don't often get wins like that, but at any rate, so this particular routine, VNet rewrite 1 header and its friend VNet rewrite 2 headers, are both pretty darn smart about 14 octet rewrites. At any rate, that's a pretty good initial survey of the IP4 and IP6 FIBs and kind of how they operate in general. At this point, you should know where to go look in the code to start making more detailed sense of it. Hope that's helpful. Thanks a lot.